Right. So today we'll talk about a method that we can use to approximate the value of ARL1. So far, I've told you about a method to find out the value of small k. I have also discussed some ideas on how to estimate the value of h, but I've not talked about how we can actually calculate the value of ARL, right? In all of the problems so far, we have just constructed our control limits. That's all. So today we'll focus on a method that's called Sigmund's approximation. And this method gives us the value of ARL1. Right, so let's start by looking at one-sided CUSUM ARL1. Right, when I say one-sided, I'm basically trying to say that you are just plotting CI plus or you're just plotting CI minus. Right, so this is either CI plus or CI minus. Okay. Now, if you go back to the example that we did, these are one-sided CUSUM control limits, right? We have CI plus as one control chart, and we have CI minus as another control chart. But if you plot them together, that's when we call this as a two-sided CUSUM chart, right? So we'll see how to estimate the value of average run length in each of these two cases. Right. So first, let's start with the one-sided CUSUM ARL. For one-sided CUSUM ARL, we will have two values of ARL. One for the upper CUSUM chart and the other for the lower CUSUM chart, right? So I'm going to call this as ARL plus and ARL minus, all right? So ARL plus or ARL minus can be given as exp minus 2 capital delta times b plus 2 capital delta times b minus 1 divided by 2 times capital delta square. All right, this is when delta is not equals to 0. You see capital delta is in the denominator, right? So to have a meaningful value of ARL1, we need to make sure that capital delta is not equal to 0. But if capital delta is 0, value of ARL is just b square. Now, I'll tell you what are the values of capital delta and small b, right? Capital delta, let me write here, where capital delta is given as small delta star minus k. This is small k. Remember, capital K is given as small k times sigma, and capital H is given as small h times sigma. Remember this? So our capital delta, this is if you're not familiar with this, this is called capital delta. Okay, this is capital delta. And if this one is small delta. Right, so coming back, capital delta is equal to delta star minus k for CI plus. If you are trying to find out the average run length for upper CUSUM chart, you will use this value of capital delta. If you're trying to find out average run length for the lower CUSUM control chart, which is CI minus, then you will use minus delta star minus k. Right. So we know k. Let's define delta star. Delta star is mu1 minus mu naught divided by sigma. There's no absolute value here. Notice, right? Mu1 is the process mean after the shift. And mu0 is the process mean when the process is in control, right? Right, so now we have the value of capital delta. Let's also write down the value of small b. B is given as k plus, no, it's h plus 1.166. This is the value of small b. And you know that small h comes in the formula for capital H, right? Here. Right, so this gives you the value of average run length for upper CUSUM or lower CUSUM chart. Now, if you are using a two-sided CUSUM chart, in other words, if you're plotting both CI plus as well as CI minus together, then you will have average run length given as 1 by ARL is equal to 1 by ARL plus 1 by ARL minus. That will be the value of your average run length when you're using a two-sided CUSUM chart. Right, let's write down a few cases here. Any questions so far? I will present an example so that it's easy for you to understand how these values are calculated. Okay. All right, so now we have ARL for both of these two cases. Now, if you can look at delta star, it's on the right hand side of your screen. If you look at delta star is the difference between the in process after the shift, process mean after the shift, and the process mean before the shift divided by sigma. So if there is no shift in the process, in that case, delta star is equal to 0. Does it make sense? So if there's no shift in the process mean, delta star is equal to 0. And if delta star is equal to 0, the above formula will give us the above formula will give us ARL 0, right? If there is no change in the process mean, then the formula will just give us ARL 0, right? Now, if delta star is not equal to 0, that means there is a change in the process mean. This means we will get ARL 1. Now, why is this important? This is important because whenever you are trying to develop your control limits, it depends on what is the value of ARL 0. ARL 0 is something that you control, right? When we were looking at Schubert control charts, we said that we want a value of ARL 0 equals to 370. So when you want ARL 0 equals to 370, we know the alpha error, right? Alpha error was 1 by ARL 0, right? This was your alpha error, and this turned out to be 0.0027. Now, once we knew alpha, we were always able to find out Z alpha by 2, which was 3, right? And then we knew what are the width of the control limits, right? So in a similar fashion, if I know ARL 0, then I can backtrack and I can find out what will be the value of H here. And if I know the value of small h, I can always find out what will be the width of the control limit. Does it make sense? Right, so let's take a look at an example and then this will be more clear to you. Suppose that the in control process mean is 40, mu naught is equal to 40, and sigma naught is equal to 2, right? The objective here is to detect a mean shift to mu1 equals to 43. So we want to find out mu1 equals to 43. And the question also specifies that we have to maintain the in control ARL 0 370, right? It already tells us that ARL 0 should be equal to 370. Now, if I want ARL 0 equals to 370, then I have to find out what will be the value of H. If I know the value of H, I can find out capital H, which is small h times sigma, right? Now, if I go back to the table that I showed you the last time, if H is equal to 5, ARL 0 is 465, right? Which is a little higher than what we want. We want 370. And if H is equal to 4, then ARL0 is equal to 168. So definitely the value of H in our case will be somewhere in between 4 and 5. But we still don't know what is the exact value of H, right? And unfortunately, we don't have any formula to calculate H directly, right? In Shewhart control chart, which I just showed here, this one, uh, in Shewhart control chart, we knew how to calculate the value of the width of the control limits, right? But in CUSUM chart, we don't have such formula. So what we will do here is we will use simple trial and error, right? We'll plug in the value of H, we'll assume a value of H, plug that value in the formula, and then we'll find out the value of ARL0, all right? So let's try to do that. Let's say I know the value of H should lie somewhere between 4 and 5. Let's assume that the value of H is exactly equal to 3.5. It's somewhere in between 4 and 5, right? Now, we want to find out ARL0. So if you go back here, to find out ARL0, we have to assume delta star equals to 0, right? So let's put this here. Delta star is equal to 0, right? We have these two values. And we also know that capital K is equal to small k times sigma, right? And we had the formula for capital K from previous class, which is 1 by 2 absolute value of mu1 minus mu0, right? We know.
Professor,
Mhm.
H should be 4.5, not 3.5. H.
Yeah, right. Oh, no, no, sorry. I think I made a mistake here. So sorry about this. So this is the chart for K equals to zero point 0.5. In our case, I think K will be slightly different. If we calculate, let's actually just let's forget H for the timing. Okay, let's write down what we know in this case. By the way, thank you so much for pointing this. So let's try to find out what we already have here. All right. So if we calculate the value of capital K, this will be 1 by 2, 43 minus 40, which is 3, and this will turn out to be 1.5, right? And if I know the value of capital K, I can find out the value of small k. Small k in this case will be equal to 1.5 divided by sigma naught, which is 2, and this will be equal to 0.75. So that's the mistake I made. In this case, value of small k is 0.75. In the table that we have here, the value of small k is 0.5. So we cannot assume that it lies somewhere between 4 and 5. That's completely my mistake. So let's just assume I did some calculations and I started with 3.5. So let's actually start with 3.5, right? So let's start by setting the value of H equals to 3.5. Definitely, if the value of K was 0.5, then we can actually use that table as a reference and pick the value somewhere between 4 and 5. Right. So now we have these values with us. Now, if you go back to the formula for ARL here, we need two parameters. We need small b and we need capital delta. Small b is easy. Small b is just h, which is 3.5 plus 1.166, right? So this will be 4.466. Now, capital delta is actually, there are two possible values for capital delta, right? The first value is when we are looking for CI plus. In this case, it is equal to minus, no, just delta star minus K. And if it is for CI minus, it is minus delta star minus K. But right now, delta star is equal to 0. So our value of capital delta is equal to minus K for CI plus and CI minus, right? It will be the same for both upper CUSUM chart and the lower CUSUM chart. So the value of capital delta is minus 0.75. Right. Any questions so far? So we have found the values of our parameters that are needed for finding out the value of ARL0. Right. Now let's just plug and see what happens, what we get here. So I will start plugging in the values. ARL plus will be equal to exp. Now also notice here that capital delta is not equal to 0, right? Capital delta is not equal to 0. So I can use the first formula for ARL plus minus, right? So this will be exp minus 2 times delta, which is minus 0.75, times b, which is 4.466, plus 2 times minus 0.75 delta times b, and b is 4.466 minus 1 divided by 2 times delta squared, right? So I've plugged in all the values here, and if we calculate this value, you will get approximately equal to 966. All right, so now let's find out ARL minus. For ARL minus, also we use the same formula. The only thing that is different is capital delta, right? But since we are calculating ARL0, and for ARL0, capital delta is same for CI plus and CI minus, so ARL minus will also be equal to 966. Make sense? All right, so once we have ARL plus and ARL minus, we can find out ARL 0 equals to 1 by ARL plus 1 by ARL minus. Right? And if you calculate this, you will get 400 and I think 83. Yeah, so you'll get 483. Now,
Professor,
yeah,
I thought we were calculating ARL1 for this because
right,
there's a mean shift.
right. So I think you missed the first point here. If you want to find out ARL1, you first have to define what are your control limits. In this case, you have to find out the value of H here, right? This was the first thing that I mentioned. You have to first of all find out capital H. To find out capital H, you need to find out small h, right? And to find out small h, I'm going to use this reference here, which is ARL0 equals to 370. Okay, so I'm using a trial and error method here. When I used a value of 3.5, h equals to 3.5, I got a value of ARL0 equals to 483, which is a little higher than 370. So I'm again going to make some modifications to small h. I'm going to assume slightly lower value of h, right? Let's say h is equal to 3.32, right? Now, when I use h equals to 3.32, in this case, b will be equal to 4.486, right? And delta, which is capital delta, it will still be minus 0.75, right? Nothing will change. I've only changed h here. In the previous case, I used a value of h equals to 3.5. Let me just mark here. Now I'm using h equals to 3.32. Now if I use h equals to 3.32, again I can calculate ARL plus, which is equals to exp minus 2 minus 0.75, now times 4.486. Did I make a mistake somewhere in calculations? Can anyone find an error here?
Yeah, your calculation for the first B is wrong.
Yeah, that's what I'm observing here. So this will be 4.666, but 966 is right because I made the calculations before the class. So that will be correct, except that this needs correction here. 466, and this will be 466. Is that right? Okay, so now I have, now I'm working with h equals to 3.32, and I have the value of b. So I'm just plugging in these values, plus 2 times minus 0.75, 4.486 minus 1 divided by 2 times minus 0.75 squared. Now, if you calculate this value, you will get 714.6. Right? Now, I have ARL plus. Because of symmetry again, ARL minus will also be equal to 714.6. This means ARL1, sorry, ARL0 in this case will be 1 by 714.6 plus 1 by 714.6 and inverse of this, and this will give us 368.3. Let me see if I did everything right here. There's a lot of numbers. I didn't, so I again made a mistake here. So this number is not 714, but this number is 736.5. And so this will also change. This will be 1 by 736.5 plus 1 by 736.5. Can someone quickly calculate the value of ARL0? Can someone quickly calculate 1 by 736.5 plus 1 by 736.5 and take the inverse of that? And tell me if it is exactly equal to 368.3 or not.
Yes, Professor, this one's right.
Thank you so much. Right, so we have got the value of ARL0. Now this value of ARL0 is actually pretty close to the value of 370, right? This is very close to 370. Now you can do some more trial and errors and find out the exact value of H that will give you ARL0 equals to 370. But for the time being, I'm gonna stop at 3.32. So now I have the value of small h. Now I can write down capital H is equals to small h times sigma, right? I don't need to write capital H because you don't need capital H to calculate ARL1, but I'm just writing it down here so you know what are the control limits we're using. Times sigma is 2. Sigma is 2, right? Yeah, sigma is 2. So you get 6.62, right? Now I have the value of H here. Now let's calculate ARL1. Now to calculate ARL1, we have to first of all calculate ARL plus. To calculate ARL plus, we need delta for CI plus, right? Delta for CI plus is delta star minus K, right? Delta star, we already have the value of delta star, which is mu1 minus mu0 by sigma, right? So let's write down the value of delta star. Delta star is equals to 43 minus 40 divided by 2. So this will be equal to 1.5, right? So I can write down capital delta equals to 1.5 minus K was equals to, what was the value of K? K was equals to 0.75 here, right? So 0.75. This will give us 0.75 for CI plus. So I'm just focusing on the upper control, upper CUSUM chart right now. The value of capital delta is 0.75. And b, we already have the value of b, which is equals to h plus 1.166, which is equals to 3.32 plus 1.166, and this will be equals to 4.486. Any questions so far? So let's plug in the values and we'll get the answer by using the formula for ARL plus. This will be equal to EXP minus 2 times delta. Delta is 0.75 times B, which is 4.486, plus 2 times delta, which is 0.75 times 4.486 minus 1 divided by 2 times 0.75 squared. If you calculate this, you will get 5.11. Right. Similarly, you can calculate ARL minus, which will be for ARL minus, we need the value of delta for CI minus, which is minus delta star minus K. So this will give you minus 1.5 minus 0.75. This is equals to minus 2.25 for CI minus, right? And B remains same, whether it is ARL plus or ARL minus. So we will plug this value in again. So it is EXP minus 2. Delta is minus 2.25 times 4.486, close the bracket, plus 2 times minus 2.25, 4.486 minus 1 divided by 2 times minus 2.25 whole square. And if you calculate this, you will get this equals to, I think it's a very large number. It's 5.28 into 10 to the power 7. All right, so now once we have the values of ARL plus and ARL minus, we can finally calculate ARL1 equals to 1 by ARL plus 1 by ARL minus. And this will give us 1 by, sorry, it will be 1 by ARL1. So this will be 1 by 5.11 plus 1 by, this is a very large number, right? So we can approximately say that the second term is close to 0. So we can ignore this. And this will give us ARL1 equals to 5.11, approximately equals to 5.11. All right. So this means that if we want to detect a change from mu0 equals to 40 to mu1 equals to 43 using a CUSUM chart, ARL1 will be equal to approximately equal to 5.11. Any questions so far on this one? If there are no questions, I will ask a bonus question. Just arrange this. Okay, so let's ask a quick bonus question here. Can someone tell me what does the value of ARL minus mean here? The value of ARL minus, as you can see here, is very large, right? What does it actually mean in this example? I will give you marks even if you try, so don't be hesitant if you are wrong or if you're not right.
Professor?
Yep.
I think the process is shifting towards the positive side. That's why
Right.
there's a very less chance of going to the downside of the mean.
Right.
So that's why.
Yes. So did everybody get that answer? right? If there's a dead silence, I'm going to assume that everybody got that answer. But just for the sake, I'm going to repeat. If you observe this question, the mean shift is going from 40 to 43. There's an upward shift, right? So the shift can only be detected by the upper CUSUM chart, right? The lower CUSUM chart cannot detect this change. That's why the value of ARL minus is so large. Good, awesome. This is good. So this concludes the calculation of ARL 1 and ARL 0. It's a little complicated, not complicated, I would say mechanical work, but I would strongly recommend you to go through each of these steps, because if you miss one of these steps, you might not get the correct answer in the exam. So practice a couple of times so you get it right. Right, let's close CUSUM chart. So far, we have talked about CUSUM chart when the value of n is equal to 1. Many a times, your value of n can be more than 1, right? When it is more than 1, instead of using xi, we will use xi bar, right? Where xi is nothing but sum of xj, x, xij, j equals to 1 to n divided by n, right? And similarly, instead of using sigma, we'll use sigma x, which is sigma by square root of n, sigma x bar, right? Second point is we can use a one-sided CUSUM chart. In many scenarios, there's always shift in one direction. And that happens a lot. I gave you some examples, right? It was the water contamination example. If you're looking at the content of lead in water, you always want to check when it exceeds a certain threshold upwards, right? So in that case, you may want to just use C plus. There are examples where you want to just use C minus. And another thing to note here is CUSUM is extremely efficient when the change in the process mean is extremely small. If it is very tiny shift, you can detect it by using a CUSUM chart. On the other hand, Shewhart chart is good when you're trying to detect a change with a very large magnitude. Any questions on this one? I would recommend you to read pages from 424 to 433 of the reference book. I just want you to read because, as I mentioned, CUSUM's chart did not ended with page in 1954 or 1961. There were a lot of researchers who were continuously working on improving the CUSUM chart, finding out methods and algorithms to estimate ARL1, ARL0. So research has been continued for, I think, 20, 30 years. So these pages, they actually summarize some of the other developments in CUSUM chart, which I think it's not feasible to cover in class, but I would highly recommend you to go back and read yourselves. Right, so now we have seen a CUSUM chart. Another type of control chart takes that also takes memory into consideration, it's called exponentially weighted moving average, or EWMA. Right? The concept is similar. We want to take into consideration the past data to plot our control chart. Okay. And this one is called EWMA. Let's start by writing down the EWMA statistic. EWMA statistic is defined as ZI, and it is equal to lambda times xi. Xi is your current measurement, plus 1 minus lambda times zi minus 1. Now you can observe very clearly here that zi minus 1, the second term, this is capturing the memory, right? And the first term is just your current observation. Current observation. Right? Now you have here a parameter lambda, which is a user specified parameter. and the value of lambda always lies between 1 and 0, right? Okay, so there's one more thing here. We want to make sure the value of 0 is known to us, z0, and z0 will be equal to mu 0, right? So you can initialize the exponentially weighted moving average control chart. Now, you might be thinking that the ZI statistic, the EWMA statistic, is called exponentially weighted moving average, but there's no exponential term here, right? You might think about this. So to understand EWMA a little bit better, let's try to rewrite this. Okay, what I will do here is I will just try to expand this a little bit more. So Zi is equals to lambda times xi plus 1 minus lambda times Zi minus 1, right? This is the initial formula. Let's see if we can write this in this form. 1 minus lambda, and we will write down the value of Zi minus 1 in terms of xi. So this will be equal to lambda times xi minus 1 plus 1 minus lambda times Zi minus 2. I can do this, right? I have just written down the formula for Zi minus 1. And this gives us lambda times xi plus lambda into 1 minus lambda times xi minus 1 plus 1 minus lambda square Zi minus 2, right? So if you keep on expanding this, you will get lambda times xi plus lambda times 1 minus lambda square. No, this will be as is xi minus 1 plus lambda times 1 minus lambda square xi minus 2 plus 1 minus lambda cube Zi minus 3. So you can see the trend here, right? We can keep on writing this as long as we want. And let me just extend the page here. Okay. No, this is not good. How do I extend the page? Okay, this is good. All right, so now we can keep on writing this. If you keep on writing this, you will realize that this turns out to be lambda times summation j equals to 0 to I minus 1 minus lambda to the power j xi minus j plus 1 minus lambda to the power I z0. This is what you will get at the end. Now, if you observe this last term here, let's try to focus on this last term here, this one, the one that I have underlined right now. If you observe this one, xi is our current observation, right? Xi minus 1 is my previous observation. Xi minus 2 is the previous to previous observation. So starting from the second term onwards, these are all our historical terms, right? Historical terms. In other words, this is our memory. Now, if you look at the historical terms, they are weighted by this term lambda 1 minus lambda to the power j. Right? You can actually even ignore lambda here. You can just focus on 1 minus lambda to the power j. Now, this term is an exponential term, right? Lambda is less than 1. So if lambda is less than 1, as j increases, the value of this exponential term will keep on decreasing exponentially. All right? So that's why it's called an exponentially weighted moving average. As you go back in time, the weight keeps on decreasing exponentially. So let me write this down. As you go back, what I mean by going back is basically I minus 1, I minus 2, I minus 3, and so on. The weight decreases exponentially. And that's why it's called an exponentially weighted moving average. Any questions? Let's quickly compare EWMA and CUSUM. It's a quick comparison here. So for EWMA, what we just saw is we can write down Zi as equal to summation lambda summation of 1 minus lambda to the power j xi minus j, and you sum from j equals to 0 to I minus 1 plus 1 minus lambda to the power I z0, right? This term here, this first term tells you that this is an exponentially weighted exponential term. So it's exponentially weighted, right? Now, if you go back to your CUSUM chart, you remember CUSUM chart, we used to write down CI. Let's ignore CI plus and CI minus. Let's just stick to CI. Okay, if you remember the value of CI, this was equal to xj minus mu naught summation j equals to 0 to I minus 1 plus you have xi minus mu 0, where the second term is your current observation and the first term is your memory. Now, if you look at the past terms, the memory, there is no weight, right? There's no weight attached to xj minus mu naught. So that's the major difference between CUSUM and EWMA. There's no weighting done. There's no weighting here. So there's no weightage to previous terms, right? And in EWMA, we have an exponential weightage to the previous terms. Does it make sense? All right. So now now we have ourselves the exponentially weighted average moving chart. We know we can plot the value of Zi and we can monitor the process, but we need the value of upper control limit and the lower control limit, just like our previous cases, our previous examples, right? So let's start by writing down our control limits. Now, to find out control limits in EWMA, we'll make some assumptions here. Okay, let's start with the first assumption. Our first assumption is that the observations that we are taking in, they are independently and identically distributed, and they follow a normal distribution. So let's say our observations x1, x2, up to whatever we have, this follows a normal distribution with some mean and some sigma square. I don't know the value of mu and sigma square, but let's assume it follows a normal distribution. And these values are also IID, independently and identically distributed. All right. Now, if you remember lectures 5 and 6, we worked a lot on Shewhart control charts, and we were making the models for Shewhart control charts, and we realized that for Shewhart control chart, we need the value of mu and we need the value of sigma to develop the control charts, right? And that's pretty similar in the case of EWMA also. To develop the control chart, we need the value of the mean and the value of the variance of Zi. So in the next few minutes, I'm going to talk how we can calculate the values of mu and sigma, right? Let's start by again writing down the expression for Zi. Zi is equal to lambda summation 1 minus lambda to the power j x I minus j, j equals to 0 to I minus 1 plus 1 minus lambda to the power I z0, right? Now, if I want to write down the expectation of zi, I can write this as lambda is a constant, right? So I can take out lambda, and 1 minus lambda to the power j is also a constant. So I can just write this as 1 minus lambda to the power j, and then I have expected value of xi minus j. Makes sense? I have taken out all the constant because expectation of a constant is just a constant. Plus, this whole term is a constant here, right? And we also know that the value of z naught is equal to mu naught. So I can just write this as 1 minus lambda to the power I times mu 0, right? Okay. So now, if I assume that expectation of xi minus j is mu, then I can simplify this as lambda times mu summation of j equals to 0 to I minus 1, 1 minus lambda to the power j, plus 1 minus lambda, 1 minus lambda to the power I times mu naught. Right? That gives you the mean of zi. Now, can anyone tell me what happens when the value of I goes to infinity? What will be the value of expectation of zi if I goes to infinity? Is anyone doing the calculation? No? Okay, let's do the calculation here. If I goes to infinity, expectation of zi, let's see how we can calculate this. If you look at the second term, it's 1 minus lambda to the power of I, right? And lambda is less than 1, less than equal to 1. So this term exponentially decreases, right? So if I goes to infinity, this term will go to 0, right? This term will go to 0, and we only have then left lambda times mu summation of j equals to 0, and I goes to infinity. So I'll plug infinity here, and it's 1 minus lambda to the power j. The second term is nothing but an infinite geometric series, right? So if you sum an infinite geometric series, you will get lambda times mu multiplied by 1 minus 1 minus lambda. That's the sum of a geometric series, right? Now, if you calculate this, you will just get mu as the expectation of zi, right? So if I goes to infinity, expected value of zi is nothing but mu, okay? And if our process is in control, we can say that this is mu is equal to mu naught, right? This is when the process is in control, remember? So now we have the value of zi, the mean of zi. Now let's look at the variance of zi. It will be exactly similar way, except that for the constants, you will take the square of all of the constants, right? So let's again write this down here. Zi is equal to lambda summation of j equals to 0 to I minus 1, 1 minus lambda to the power j xi minus j plus 1 minus lambda to the power I multiplied by z0. Now let's write down the variance of zi. Now observe, lambda is a constant, so I'm going to write down, let me just quickly arrange this here. Okay, so lambda is a constant here, so I will do lambda square. 1 minus lambda is also a constant, so I'm going to take another square. This will be j equals to 0 to I minus 1, 1 minus lambda square, and then j. So it will be 1 minus lambda to the power 2j. and then I will have variance of xi minus j, right? And then we will have, what will be the variance of the second term? Anyone? Variance of the second term is just 0, right? Because z naught is a constant. Remember, z naught is nothing but mu naught. This is just a constant. And 1 minus lambda to the power I is also a constant. So the second term is just 0, right? So we can write this as, and variance of xi minus j, we can take this as sigma square. So this will be equal to lambda square sigma square sum of j equals to 0 to I minus 1, 1 minus lambda to the power 2j. Any questions on this one? Right. So now we have the variance of zi. Let's do a little bit of simplification here so that we have a nice looking expression. This is again a geometric series with finite number of terms. I'm not taking I to infinity right now. We'll wait for that. But if there are finite number of terms, we can use the geometric sum and we can write this as lambda square sigma square. Geometric sum is nothing but 1 minus lambda to the power 2j divided by 1 minus lambda square. Right? Now we can do a little bit of simplification here, and this will give us sigma square lambda divided by 2 lambda, and this will be 1 minus lambda to the power 2j. That's a little bit of simplification here. So that's the variance of zi. Now in statistical literature, this is also called time varying variance. All right, it's called time varying variance. Now let's try to put limits on, I think I made a mistake here. This should not be j, this will be I here. Let's correct this because we have taken sum over j, right? So this will be I here. And similarly, this will be I here. Now let's put limit on I. Let's say I goes to infinity. Now variance of zi when I goes to infinity, this will be equal to sigma square lambda by 2 minus lambda. If you look at the second term inside the bracket here, the second term, this one, this will go to 0 if I goes to infinity, right? So if this goes to 0, I just have sigma square lambda by 2 minus lambda. And this is also called as steady state variance. All right. Any questions? Now we have the value of mean and we have the value of variance. So now we can write down our control limits for EWMA. Control limits in EWMA is much more simpler than what we saw in CUSUM. Okay, so it's slightly better. We actually have a formula for calculating the control limits in EWMA. For upper control limit, first, we will look at time varying control limits, okay? When I say time varying control limits, that's when we use time varying variance, all right? So for time varying control limits, UCLI will be equal to mu naught plus L. L is a constant that is typically equal to 3, just like Shewhart control chart. L times sigma, I'm just going to plug in the value of variance here. Okay, this is equal to lambda divided by 2 minus lambda multiplied by 1 minus lambda 2 to the power I. Okay. So this gives us UCLI. And similarly, LCLI is equal to mu 0 minus L sigma square root of lambda divided by 2 minus lambda 1 minus lambda to the power 2I. That's your lower control limit. And your center line is just your mu naught. Right? That gives us the time varying control limits. And when it talks about steady state control limit, that's when I goes to infinity. So when I goes to infinity, you have UCL slash LCL equals to mu naught plus minus, this will be L times sigma square root of lambda divided by 2 minus lambda, right? The second term inside the square root is just 1. All right, any questions on this one? Right. When I say I goes to infinity, I really don't mean that I goes to a really, really large number. As long as I goes to 30 or 40, you will see, not even 30 or 40, even if it goes to like, I don't know, 20 or 25, you will see that the time varying control limit will be close to the steady state control limit. What I mean by that is when I goes to 25 or 20, I goes to somewhere between 25 to 30, the second term will automatically become very, very close to 1. And we'll see this in the example now. All right, any questions so far? Right. Let's take an example here. Let the in control process mean be mu naught, which is 20, and sigma is equal to 1, and n equals to 1. We will try to detect a mean shift of 1 standard deviation in the process mean. So somewhere in this chart, I have done a 1 standard deviation shift in the process mean. Let's play the guessing game today again. Can anyone guess again where the mean shift is happening? And then we'll check.
Around 12, Professor.
12? Here?
Before that, right after 10.
Okay.
Where it's
Okay. Any other guesses?
Around 30.
Around 30.
Any other?
then at 20, maybe.
Okay. Any other? I think we can keep guessing here, but good. I think one of this is correct. One of this is for sure correct. So last time I forgot to give you the data. This time I thought I'll just copy it here itself. You can see the data, and I'll also upload this on Canvas. This is your XI. Okay, this is what we need to construct our control chart. These are really tiny, so I'm gonna zoom here a little bit so you can see. XI is given here, and if you want to construct the EWMA chart, you also need the value of lambda. Remember, in this case, I have fixed the value of lambda to 0.25, and I have just taken it arbitrarily right now. I will talk about how to find out the value of lambda. Right? So once you have the value of lambda, you can start calculating Zi, right? So Z1 will be equal to 0.25 times X1, which is 20.7318, plus 1 minus lambda, which is 0.75 multiplied by Z0, right? Z0 equals to mu naught, and mu naught is 20. So this will be 20, right? If you calculate this, you will get the value of Z1. Now, I don't have a calculator, and neither did I did the calculations, so you'll have to figure this on your own. In fact, go back, when you go back, after the class, not go back home, but after the class, Try to find out the values of Z1 up to Z40 yourselves, so you're comfortable calculating these values on your own. But what I did instead was I calculated these values and I plotted them on a control chart, right? So these values that you see here, these are actually the values of Zi. So on the x-axis, it's your Zi. No, it's not x-axis, it's actually y-axis. This is Zi. X-axis is just your samples. We have 40 samples. Now, if you look at the control limits, the center line is at 20, right? Because our mean is 20. The lower control limit and the upper control limit are a little bit fancier. Why they are fancier? As I told you, we actually use time varying control limits, right? We're using time varying control limits. And as soon as you reach somewhere around, in this case, I think it's around 16 or so, you will notice that your upper control limit and your lower control limit are now reaching a steady state value, right? So as I was saying this earlier, you don't need a really large number of values. All you need is probably maybe 20 or 25 samples, and then your control limits will reach the steady state. Okay. Now, after plotting this, you will notice that the control chart is indicating a shift somewhere around, I think this is 34, 34, 35, 36, 37, 38, 39. No, this is 35. So at sample 35, it is indicating a shift. But in reality, the shift actually happened at 30. So whoever told 30, you just won $1 million. I don't have that because I'm a faculty member. So this is where, no, let me write it this way. So after 30, mu is actually equal to 21. And before 30, mu is actually equal to 20. Make sense? Now, I think we still have some time, so I thought maybe it would be better to show you how to do EWMA on jump. So let me quickly open the example here. File, open. Oh, by the way, I didn't actually talk about the control limits here. Completely forgot. So let's actually calculate the control limits quickly. So in this case, I'm just going to calculate the steady state values, okay? You can calculate the time varying values yourself. Steady state is UCL equals to mu naught plus L. In this case, again, another parameter was L, which is 3. I've just taken 3 in this case, times sigma square root of lambda divided by 2 minus lambda. This is the formula, right? Yeah, this is the formula. So this is equal to 20 plus 3 times sigma is 1, square root of 0.25, 2 minus 0.25 is 1.75. And I think if you calculate this, might have the value here. This is equal to 21.134. And similarly, your LCL is approximately 18.866. Right, these are steady state values. These are when the control limits stabilized. Okay, so go back and you can calculate the time varying control limits as well. So let's quickly go back and take a look at the example using jump. I have the CUSUM example here. And so it's a little tricky here when you do EWMM. So why is it tricky? I will actually set up some stage here. When we were doing Shewhart control chart in jump, we just took the data and did our control chart. We constructed our control chart, right? We go to analyze control charts and whatever control chart you want to draw. Now, in this case, I don't know if the data is in control or not. Does it make sense? In Schuhart control chart, we actually knew that whatever data we are using is in control, and we just use that data to construct our control charts. In this case, we have the whole data and we don't know exactly where the process changed. So what I will do is I will try to provide some additional information. So let's go to analyze, let's go to quality and process, let's go to control chart. Um, Wait a second, where is EW? Okay, it's here. So let's go to control chart and click on EWMA. Once you are here, select the process as your observations. Your weight, I provided weight as 0.25. So let's do 0.25 here. And K sigma is your L. So L is equal to 3. Now, you have to provide the sample size, which is 1 in this case. So let's provide sample size.
Lunch. 8.99. Okay, thank you very much.
Byron, what is that? Right. Okay, I'm just gonna assume that you didn't say anything. So you specified these values. The last thing that you want to specify here is click on specify stats. Now, if you click on specify stats, you have a couple of options here. You can specify the sigma and the mean when the process is in control. Now we know these two values, right? So let's specify the value of sigma, which is equal to 1, and mean, which is the in control process mean, and we know that this is equal to 20. So we specify these values, right? Once we specify these values, click OK, and now you will get your control chart. And now you can see that the values starting 35 are exceeding the control limits. Make sense? If you don't specify those limits, what it will do is it will automatically assume that all the data points that you gave to the, I don't know, to jump are all in control. And then you will not get the correct control chart. So it's extremely important. Either you make sure that the data that you're using is in control, or you know the mean and the standard deviation of the process when it was in control. Any questions on this one so far? Now let me talk about one quick thing and then we'll end EWMA control chart. We saw this in CUSUM as well. There are some, I call this as fudge factors. You can call this anything you want, but there are always certain parameters that you have to pick as to construct these control charts, right? In the case of EWMA, you need lambda and you need L, right? You need these two parameters. Now let's try to understand a little bit about what these two parameters are so that we can pick the correct values. Not correct, but I don't know, meaningful values for lambda and L. Now, if you let's write down the value of Zi here just for the reference so that we understand where lambda is coming. So lambda is coming in this equation, right? Now, if you plug in the value of lambda equals to 1, the second term is equals to 0, right? This term will be equal to 0 if lambda equals to 1, right? And if second term goes to 0, there's no memory left. If there's no memory left, this is nothing but just your Schuhart control chart. So when lambda equals to 1, this becomes what we call as memoryless, right? And EWMA is equivalent to EWMA is equivalent to Schuhart control chart. Right? Now, when lambda is large, when you put a very large value of lambda, what you're doing is 1 minus lambda becomes really small. If 1 minus lambda becomes really small, that means you are giving a very small weight to the previous observations, right? If you give very small weight to previous observations, you basically have a short memory. So when lambda is large, you have a short memory. And a short memory is good for detecting large changes. A short memory is good for detecting large changes. Similarly, when lambda is small, 1 minus lambda is large. If 1 minus lambda is large, you are giving a lot of weight to the previous observations, and then your process gets a longer memory. A longer memory, right? And a longer memory is good if you are trying to detect small changes. Detecting small changes. Make sense? So this is how you choose the value of lambda. Now, when you come to L, you can just pick L equals to 3 to comply with our standard formulations that we have so far, L equals to 3. But many a times it is recommended that if lambda is less than equals to 0.1, if lambda is really small, then you might want to pick the value of L somewhere between 2.6 and 2.8. These are just recommended values. There's nothing special about them. Give me a couple of more minutes. I want to talk about this table here quickly. So again, based on some simulation studies, people have found out the value of average run length for different values of L and lambda. So if you look at the first row here, first row gives different values for L and different values of lambda, right? The second row here, which is shift in the mean is 0. This will be corresponding to ARL0, and all the following values will be corresponding to ARL1, right? So if the shift in the mean is 0, your ARL0 is 500 for all of these cases. And then for different values of the shift in the mean, you can calculate the value of ARL1 by looking at this table. Make sense? Now there's a quick comparison here that I wanted to do. I want to show you that EWMA and CUSUM can actually have similar performance in many cases. And one instance is this here. If you pick H equals to 5, focus on the second table here. If you pick H equals to 5, and if there is 1 sigma shift, if there is 1 sigma shift, this is corresponding to this row here, right? The value of ARL1 in this case is 10.4, right? And the value of ARL0 in this case is 465. Now, if you go to EWMA CUSUM EWMA chart, again, go to 1 sigma shift and go to the column which is second to the last. You will get the value of L equals to 2.814 and lambda equals to 0.1. In this case, ARL1 is 10.3, right? So for 1 sigma shift, ARL1 is equal to 10.3 and ARL0 is equal to 500. So you can see that if H equals to 5 in CUSUM and if L equals to 2.814 and lambda equals to 0.1, then CUSUM and EWMA, they will perform very closely, right? So these are some tables that you might want to, keep in your toolbox whenever you are doing some modeling or some research or maybe working for an industry. You will know what are the values of ARL0 and ARL1 for different values of the parameters lambda, L, or H. All right, let's stop here. It's almost end of this lecture. I don't have much to cover here. There's just one quick variation of exponentially weighted moving average. It's called moving average. And I will talk about that maybe on Monday.